Guys, welcome back to the QST YouTube channel. We're doing chemistry for six. We show the following mixtures can be separated using filtration. Sand and water, as filtration is for insoluble solid with liquid. It is required to heat a beaker containing some alcohol. How should this be done safely? Okay, so alcohol is ethanol. Ethanol is highly flammable, so anywhere near flame is highly dangerous. So to do it safely, it's best to place the alcohol in a beaker in a water bath and heat the water electrically. Which of the following statements define sublimation? Sublimation is from solid to gas, so it is a change from solid to gas directly without passing through the liquid state. Which of the following are steps involved in the separation process to obtain dry sand and dry salt from a mixture of sand and salt? So, first off, we have to add excess water and stir to dissolve all the salt. And then we have to carry on filtration to separate the sand as a residue on the filter paper and dry the sand in an electric oven. So we dissolve the salt in the water and then we filter the sand to separate the solution of salt and then sand. And then we carry on crystallization to obtain the dry salt from the filtrate. Sugar dissolves in water and alcohol, and salt dissolves in water but not in alcohol. Which of the following are steps involved in the separation of a mixture of salt and sugar? So first you have to add excess alcohol to the mixture and stir. So when you do that, sugar will dissolve in alcohol but salt will not. So the salt will be separated. So you can just filter the salt and you'll get the salt and sugar separate. And then heat the solution of the sugar to crystallize the sugar using an electric heater. That way you have the salt and the sugar separated. The apparatus needs to perform a distillation. Distillation, just memorize this. We need a thermometer, condenser, and a Bunsen burner. The liquid collected at the end of the distillation is called distillate. Yes, that is the liquid, the water or the liquid. Yeah. Whenever two liquids at boiling points that are close together are to be separated, fractional distillation is used. Fractional distillation is whenever you have close boiling points. For example, ethanol and water, for example, that is, they have close boiling points, so they are separated by fractional distillation. A long tube containing obstacles and cooled only by air is called a fractionating column. There's a picture later in the quiz to show you what a fractionating column is. But yes, memorize this. It is a long tube containing obstacles and cooled only by air. A beaker containing an ethanol solution should never be heated using a Bunsen burner because a Bunsen burner, like I said, ethanol, it's highly flammable. So a Bunsen burner, it's going to be dangerous because it's directly under the solution. The flame is under the solution. Which of the following techniques is used to separate black ink into components? To separate black ink into components, we use paper chromatography, and that is what is shown in the fourth picture. Copper sulfate can be separated from its solution by crystallization. Yes, copper sulfate is a form of salt, and we can easily use crystallization on this. Okay, this one, a second. Okay, now we're gonna need to do the moles MCR. So 1 second. Alright, so here we're gonna have to find the moles. First off, they want the number of moles of chlorine reactor. We have 14.2 grams of chlorine, and its chlorine is diatomic, so the molar mass is 70. We do 14.2 over 70. We get 0.2, so 0.200. Yes, and then we need the moles of sodium chloride produced. So for that, we do MCR. We have 1 mole, 1 to 2, so we have 0.2. This is going to be 0.4. So NaCl, we have 0.4 moles of NaCl. Find the mass of sodium chloride produced. Mass of sodium chloride, we have to do, we know that N is equal to M over M. Since N is equal to M over M, we know that mass is equal to N times M. So we have sodium chloride 0.4 moles multiplied by the molar mass, which is Na plus Cl. So 23 plus 35.5 multiplied by 0.4 gives us 23.4. Okay. This is balancing. Balancing, we have, let's see, we're gonna start from scratch. Okay, we have H2O2 decomposes into water, H2O, and oxygen gas, O2. Okay, now how many atoms of hydrogen we have? We have 2. Oxygen, we have 2. Over here we have hydrogen 2, oxygen 1 plus 2. Okay, now hydrogen is balanced, so we need to balance oxygen. So the only way here is multiply by 2 on this side and 2 on this side. That gives us 2 plus 2, and this makes it 4, and that will also make hydrogen 4, and over here as well hydrogen 4. That way everything is balanced. So our equation is 2H2O2 decomposes into 2H2O plus O2. And do not forget the state symbols. H2O2 is liquid, hydrogen peroxide, and H2O is water, also liquid, O2 is gas. Okay guys, for this one, student is asked to calculate the number of moles of moles and atoms in a sample of 17.6 grams of propene, C3H8. So we have the grams, we have N is equal to M over M. We have N is equal to M over M. So we have 17.6 over the molar mass. We need to find the molar mass of C3H8. So that's 12 times 3, and H8, 1 times 8, so 36 plus 8, which gives us 44. So when we do that, we get 0.4. Yes. How many atoms are present in the sample? To find atoms, we have to do moles multiplied by the Avogadro number to give us the molecules, multiplied by the atomicity to find the atoms. So we have the molecules 0.4 multiplied by the Avogadro number. They gave it to us as 6.02 times 10 to the power of 23. Now we multiply that by the atomicity, which is 11. Now that gives us 2 times 10 to the power of 23 multiplied by 11. We get 2.6488 times 10 to the power of 24, which here they wrote as 2.64, but closest is 2.65, which they have given as a possible answer here. Yes. Now for this one, sample of O2 gas contains 9 times 10 to the power of 21 molecules. Avogadro's number is 6 times 10 to the power of 23. So we have the molecules. They want the moles first. So from molecules to moles, we divide by the Avogadro's number. So 9 times 10 to the power of 21 over 6 times 10 to the power of 23, we get we get 0.015. In scientific notation, that is 1.5 times 10 to the power of negative 2 moles. Okay, now how many grams of O2 does the sample contain? Now we got the moles. We know that mass is equal to moles multiplied by the molar mass. So 0.015 or 1.5 times 10 to the power of negative 2 multiplied by the molar mass, we have O2 is diatomic, so it's 16 times 2, 32. So 1.5 times 10 to the power of negative 2 multiplied by 32, we get 0.48 grams. Yes, that is it. Okay, now this one, we have mass of oxygen gas. Okay, magnesium Mg reacts with oxygen gas O2 to produce magnesium oxide. By frame, calculate the mass of oxygen gas. Need to complete. Okay, now they gave the other values. They gave that 4.8. Magnesium is 4.8 grams. Magnesium is the first one, and it produces 8 grams of magnesium oxide. So 4.8 plus the mass of O2, I'll name it X, is equal to 8. Just subtraction. X is equal to 8 minus 4.8. We get 3.2, yeah. Get stuck, oh my god. What's going on? Okay. Okay, wow, okay. Aluminium reacts with oxygen gas to produce aluminium oxide. Al2O3, the chemical equation for the reaction that takes place is, okay, and they mentioned it. Sample of 108 kilogram. Mass is always in grams, they gave it as to a kilogram. Of aluminium is reacted with excess of oxygen gas to produce aluminium oxide. What do they want? They want the number of moles of aluminium in the given sample. We have that the mass of aluminium is 108 kilogram. Now to go from kilogram to gram, we have to multiply by 1000. So 108 kilogram is 108,000 grams. So 108, we know the equation for moles, which is N is equal to M over M. So we have N is equal to 108,000 over the molar mass. Molar mass is going to be aluminium. Okay, aluminium is 27. Yes, so you have to divide that by 27. What do we get? We get 4,000 moles. Yes. Now calculate the number of moles of oxygen gas consumed by the reaction. Now here we have to do MCR. We have aluminium is 4, 2, oxygen is 3, as mentioned here, 4, 3. Okay, so 4,000, and then just cross multiply 4,000 multiplied by 3 divided by 4, we get 3,000. Okay, that's it. Okay. Oh, there's one more. Sorry. Calculate the mass in kilograms of oxygen gas consumed by the reaction. Okay, mass in kilograms of oxygen gas consumed by the reaction. Now they want the mass in kilograms, not in grams. So we have oxygen gas is 3,000 moles. Now this, we did that in grams. So we have mass is equal to N times M. We know the moles, and then the mass, molar mass of oxygen. Oxygen here is diatomic, so 32. So we have to 3,000, which is the moles, multiplied by the molar mass, which is 32. So what do we get? We get 96,000. Now 96,000 is in grams, because that's how we found the moles, using grams, not kilograms. So to find in grams, you have to divide by 1000. So it goes 1, 2, 3, we get 96 kilogram. Yes, that's it. Yeah, 96. 2, 4, 6. Okay. Mixture of water and ethanol can be separated by fractional distillation. Like I mentioned before, fractional distillation is for close boiling points. Ethanol, water, close boiling points. So fractional distillation works here. Next one. Okay, this is what I said about fractionating column. This is the thing in the distillation process called the fractionating column. This right over here. Okay, so what does it do? It has a long vertical tube containing obstacles and cooled only by air. Just memorize that. That is fractionating columns. Okay, that's the picture that represents a technique used to separate the components of a solution of salt and water. Now here, they said separate the components, not, they don't just want one. So we can't use crystallization because that'll take away the water. So we have to use distillation. Like if they do not mention that they want to separate them both, then we don't really need to use distillation. But here they need to separate both of them, so we can use distillation. Next one, indicate how the potential energy and the kinetic energy of particles in a liquid change as the system is moved between the indicated points. Okay, so A to B in here. Okay, so whenever we have an uprising, that is an increase in kinetic energy. We know that when temperature increases, kinetic energy increases. So here, kinetic energy increases. And when kinetic energy increases, the potential energy, it doesn't change, it remains the same. But here the temperature remains the same, so kinetic energy here is going to be the same, it's going to stay the same. But what is it? Yeah, potential energy is going to increase. And here again, kinetic energy increases and potential energy stays the same. As temperature increases, kinetic energy increases, and when kinetic energy increases, potential energy stays the same, and when potential energy increases, the kinetic energy stays the same. Okay, so the only time kinetic energy increases when temperature increases, and that time potential energy is the same. Okay, that's all for this one. Yes, that is what they say here. Okay. 19. Okay, this one is balancing along with heat. Okay. Right. We have. I'm gonna start from scratch. NO reacts with oxygen gas. Okay, come on, right. Oh my god, bro. Okay. NO reacts with oxygen gas to produce nitrogen dioxide, NO2, plus 56 kilojoules per mole of nitrogen monoxide. Okay, so nitrogen monoxide is this right here. So every mole that increases for nitrogen monoxide, the heat increases by 56 kilojoules per mole. So okay, now we're gonna balance. We have nitrogen. We have nitrogen 1, oxygen 1, oxygen. Sorry, cross that out. We have oxygen 1 plus 2, and here we have nitrogen 1 and oxygen 2. Okay, so we need to balance the oxygen. Nitrogen is already balanced, but of course we're gonna have to make some changes. We can multiply this by 2, and that way we'll have 2 plus 2, which will be 4, but then this also will have to multiply by 2, so 2 and no 2, that will be the coefficient, 2 will be the coefficient. That way we have 4 oxygen on each side, and nitrogen increases by 2 here, also here, so everything is balanced here. So our equation, I'm just going to write it down once again, or actually no mind, it's on the board. We have 2NO plus O2 is 2NO2. Yes, okay, now that is the balanced equation. And now we need to find the heat. Like I said, for each mole of nitrogen monoxide, it increases by 56. So it has 2 is the coefficient. So 2 is a mole, and that is 112 kilojoules. 56 times 2. Yes. Okay, next question. This one. For this one, you have to balance. So we have Na plus excess water H2O gives us NaOH plus H2. So that is we have on this side Na is 1, H is 2, O is 1. Here Na is 1, OH, actually I'm going to do H here. H is 1 plus 2 and O is 1. Now to balance this, we just need to balance the hydrogen, but to balance the hydrogen we have to multiply this by the coefficient of 2. So 2 NaOH, that makes here Na2, O2, H as well becomes 2 plus 2. So we have Na here 2, H is 4 and O is 2. Now we need to balance oxygen and sodium here. So you have to multiply this by 2 to balance sodium. So here it's balanced, and balance this by 2 as well. So that way we have 2 over here. So it's going to be 4H and O is going to be 2. So okay, yeah, it's balanced. 2Na plus 2H2O gives us 2NaOH plus H2. And don't forget to add the state symbols. Yes, we get that as shown on the screen. Find the number of moles of sodium metal reacted. Number of moles. Okay, we have the mass of sodium is 4.6, and we have 23 is the molar mass. So we're going to have to do 4.6 over 23, which will give us 4.6 over 23 gives us 0.2. Yes, okay, number of moles of hydrogen gas released is going to be, we're going to be using MCR. So number of moles of hydrogen gas released will be 2 to 1. Mass, it's 1 here and 2 here, so 0.2 here. So it's going to be, when you cross multiply, you get 0.1 here. Yes, that's it for this one. Last one. Sample of 0.5 moles of butane gas undergoes complete combustion RTP according to the following chemical equation. Okay, number of moles of oxygen gas needed to react completely with 0.5 moles of butane gas. Okay, we have the moles of butane gas. Now we need to find the number of oxygen gas needed to react with 0.5 moles of butane gas. So we can do MCR here again. So we have butane C4H10 2 and oxygen 13 to 0.5. When we do the cross multiply, we get cross multiplication gives us 3.25. Yes, the volume of oxygen gas needs to react completely with 0.5 moles of butane gas. Okay, we found the moles, we need to make it into oxygen volume. So to make it into volume, we have the condition RTP. RTP is 24 decimeter cube mole. Okay, so we have to multiply 3.25 multiplied by 24. So 3.25, which is moles, multiplied by the RTP. So we get 24 times 3.25 is equal to 78. Yes, we have 78. Air is 20% oxygen gas. Find the volume of air needed for the given sample of butane to react completely. So if air is 20% oxygen gas, to make it 100%, so it reacts completely, we need to multiply this by 5. So 78, the volume, we have to multiply by 5. They want the volume. So just multiply 78 by 5, we get 309. Okay, next one. Okay. So this one, hydrogen gas combines with oxygen gas to form water. The reaction involves an energy change of 284 kilojoule per mole of hydrogen gas. The energy diagram of the reaction is shown below. Okay, choose the nature of the described reaction. So Whenever I want you to remember that whenever we for a substance, we are releasing energy. However, when we are breaking down a substance, we are absorbing energy, like changing ice cube to water needs heat, needs energy. So here they said nature of the described reaction. It's exothermic because it's hydrogen gas combining with oxygen gas to form water. And as you can see here, its energy is decreasing. So that means energy is being released. Yes. Now, when 1 mole of water is poured, 284 kilojoules of energy is released. Yes, like we said, it's exothermic, so it releases energy. What is the amount of energy involved in 0.5 moles of hydrogen gas are consumed? Yes, they said here 284 kilojoule per mole. And then they said here 0.5 moles of hydrogen gas. So 0.5 is half of 1 mole, so it's going to be 284 divided by 2, we get 142 kilojoules. That's it. Okay. Yeah, okay, the number of moles of zinc granules consumed in the reaction. Okay, we want the moles. We have 0.109 gram of zinc granule. That's the given mass. Now we need to find the moles. We have zinc is 65.4. That's a molar mass. So we can do 0.109 over 65.4. What do we get? Let me see. We get. I made a mistake. 1 second. Sorry, wait 1 second. No, I have not made a mistake. Okay, so three significant figures and scientific notation. The initial value is 0.001. When we do this, we get 0.00166, but then they want in scientific notation, so 1, 2, 3. It's 1.67 times 10 to the power of -3. Okay, yeah, that's it for that one. Now, next one, calculate the number of moles of hydrogen gas collected at RTB conditions. We do MCR. Now here, we have, it's 1 to 1. 1 to 1 second. Hydrogen gas collected, yes. 1 to 1. So 1 to 1 is going to stay the same. The moles is going to stay the same. It's also going to be 1.67 times 10 to the power of -3. Locate the syringe indicating the total volume of hydrogen released at RTB conditions. Okay, here we want volume of hydrogen gas. Okay, at RTP we know it's 24 as given, so we have to do moles multiplied by the volume to find, no, moles multiplied by the RTP condition to find the volume. So we know that the volume, as per given 1.67, as per we solved, multiplied by 24, we get 0.04. But that is in meter cube. Yes, that is in meter cube. Sorry, decimeter cube. Sorry, my bad. Decimeter cube. So decimeter cube, like volume is always in decimeter cube. But then if they want it in centimeter cube, we have to multiply by 1,000. Yes, by 1,000. So when we multiply the moles by 24, we get 0.04, and then we have to multiply by 1,000. 1, 2, 3, we get 40. That is from decimeter cube to centimeter cube, we get 40. Okay, there it is. That's the amount of volume. Okay. Get the balance chemical equation for the above reaction. We have to balance again. So here, Fe plus Cl2 is FeCl3. Okay. Fe on this side is just 1. Cl is 2. And Fe here is 1, but Cl is 3. Just multiply Cl here by 3 and here Fe by 2. That makes Fe here 2, Cl here 6, and Cl here 6, but then Fe is 1 to 2, so also here we have to multiply by 2, so it's all balanced. 2 Fe plus 3 Cl2 is 2 FeCl3. Yes, they don't want state symbols for this one. Now, how many moles of chlorine are needed to produce 6 moles of iron chloride? Now 6 moles of iron chloride, we can just do MCR again. So iron chloride is this one. How many moles of chlorine? Okay, so 3 to 2, 6 moles of iron chloride. So we just cross multiply, we get 6 times 3 divided by 2, we get 9. Yes, that is all. Alright guys, that's it for the chemistry quiz. Thank you very much and good luck with your exams tomorrow. Bye.